All right, so we're going to start off just by finishing up that one thing we didn't get to in section 3.1, which is how we figure out when a function is increasing and decreasing. Okay, and this is directly related to finding local maxes and mins. Okay, so on this graph, okay, I've just marked the created there.
When it goes from decreasing to increasing, you have a minimum value.
Yeah. If we switch from going down to going up, we create a minimum value somewhere. Okay, so you get a local, or it could be global, it depends on the function, minimum. Okay, so what this basically means is that if you can find your local or global mins and maxes, you can determine where a function goes from increasing to decreasing. Okay? You just have to find those points. So,
can you go back?
Yeah. So formally, the way you could say a function is increasing is you say, as x goes up, y goes up. Okay? If you really want to describe it formally, that's how you say a function is increasing. Okay? As x goes up, y goes up. And that's what I've written right here. F of x is like y. Okay? A function is decreasing if as x goes up, y goes down. Okay? So as x heads to the right, your y values head down. Okay? And that could look something like this. So any questions on what it means formally for a function to be increasing or decreasing? Okay, and a function could also be neither. Okay, think of a horizontal line. It's not increasing or decreasing. It's just constant, just flat. Okay, so if we had the work from what we did yesterday, we could do this one very quick. I don't think I saved it, so actually somebody in the notes, if you have it in your notes, it might help us. Okay, I want to look at the function x cubed minus 4x, which is the one we did in example 2. And I want to find where it goes from increasing to decreasing. Now, we already found all the local mins and maxes yesterday. Yeah?
Can you go up?
Yeah, I'm going to go back to the other page in 1 second. Yep. We found these yesterday, so we need to either find them again or just, if somebody still has them, that would be great. But if not, we'll just do it again. Okay, so find the intervals on which x cubed minus 4x is increasing and decreasing. Okay, so let me graph it first. And try to keep everything on the screen at the same time, including the calculator. All right, so x cubed minus 4x. Get rid of everything else. Okay, does anybody still need to see what's on the left part? No? Okay, so I'll cover that up with the calculator. Okay, I'm going to do zoom 6. Because I think from the problem we did in the homework, our window was at like 6,000, so that's way too high for this one. Okay, and now I want to find the intervals where that is increasing and decreasing. Right. Does everybody have those two? Okay. All right. Does anybody have this maximum from yesterday? What we found that was? Nobody has that maximum. Or if not, we'll find it again. Yeah, what is it, John?
Negative 1.5.
Negative.
Actually, it's 3.08.
All right, what's the x value first?
Negative 1.15.
Negative 1.15 and 3.08.
3.08 is the.
Now, if I remember, wasn't the other one the same thing, just the signs were flipped?
Yeah.
Okay, so this is the minimum. So that's 1.15 and negative 3.08. Okay, so now I can figure out where this function goes from increasing to decreasing. Okay, it's increasing. I'll do increasing as green from here to here and there to there. And I'll do decreasing as red going down. Okay, it's decreasing right there. Okay, so I'll do the first interval where it's increasing. That's from negative infinity up to negative 1.15. Okay, can somebody else give me the second interval where this is increasing? Ian?
And x equals 1.5, 1.15 to positive infinity.
Yeah, 1.15 to positive infinity. And we don't include 1.15 because at exactly 1.15 it's not doing either. It's not increasing or decreasing. It's just constant. All right, so we've got increasing, and now I need the interval where it is decreasing. Nick, can you give me the interval where this one is decreasing?
If x is negative 1.15
Yeah, good. 2.
to 1.15.
Perfect. And that's it. Okay, if what would happen if you had a function without any local minimums or maximums? What would that mean? Yep.
That would just be a straight line, right?
It could be a straight line, or it could also be something like this. So what would that mean about where it's increasing and decreasing? If you have no minimums or maximums. Yeah, it's either increasing forever or decreasing forever. This would be an example of increasing forever. Okay? So there is a question like that in the homework, and some people get tripped up because they can't figure out the mins and maxes, and there are none. Okay. All right, so any questions on increasing and decreasing? All right, so that's the end of 3.1, what we didn't finish yesterday. Okay, and now we'll take a look at 3.2. Okay, 3.2 looks at three different things, and you'll kind of see how they're connected, especially the first two, continuity and intermediate value. Okay, end behavior, that one's kind of on its own. It's a little separate, and I'll explain what that is when we get to it. All right, so most graphing calculators, especially older ones, assume that when you draw something on the screen, you want it to be connected. So if you have an older calculator and you type this in, this is what you're going to get. Okay, I typed in what's called tangent. You don't have to know what that is. I just want to show you how an older calculator would draw it. Okay? That's not how it's supposed to look. Okay? How it's supposed to look is like this. Okay? What the calculator was trying to do was connect each section that shouldn't be connected with a vertical line. Okay? That's why you saw all those vertical lines. Okay? On older calculators, you have no way to get rid of those vertical lines. Okay? On a newer one, I can detect what's called asymptotes, things that should not be connected vertically, and the calculator graphs it just fine. Okay? So let's try graphing some things that are connected and some things that aren't connected, and I'm going to graph them properly. Okay? I'm going to have the calculator detect asymptotes. Otherwise, some of the things I'm about to show you would have vertical lines where there shouldn't be any. Okay? So let's try graphing 1 divided by x minus 3. Okay, and what I'm going to do is I'm going to put a picture of each one of these graphs as I do them up on the screen. Okay, so I have this one. Okay, you just need to kind of understand the general behavior of it. You don't need to look at anything specific. And then I'm going to ask you a question about each of the graphs that I'm putting up. I'm going to graph what's called the integer function. Okay, this is a function that it's also called a step function. I think you'll see why in a second. Okay, almost looks like these series of steps. What the integer function does is it rounds off any number you give it to the nearest, basically, integer. That's less. Okay, so this function rounds off any number that you give it to the closest integer it can. That's less. All right, so most graphing calculators, especially older ones, assume that when you draw something on the screen, you want it to be connected. So if you have an older calculator and you type this in, this is what you're going to get. Okay, I typed in what's called tangent. You don't have to know what that is. I just want to show you how an older calculator would draw it. Okay? That's not how it's supposed to look. Okay? How it's supposed to look is like this. Okay, what the calculator was trying to do was connect each section that shouldn't be connected with a vertical line. Okay, that's why you saw all those vertical lines. Okay, on older calculators, you have no way to get rid of those vertical lines. Okay, on a newer one, I can detect what's called asymptotes, things that should not be connected vertically, and the calculator graphs it just fine. Okay, so let's try graphing some things that are connected and some things that aren't connected. And I'm going to graph them properly. Okay, I'm going to have the calculator detect asymptotes. Otherwise, some of the things I'm about to show you would have vertical lines where there shouldn't be any. Okay, so let's try graphing 1 divided by x minus 3. Okay, and what I'm going to do is I'm going to put a picture of each one of these graphs as I do them up on the screen. Okay, so I have this one. Okay, you just need to kind of understand the general behavior of it. You don't need to look at anything specific. And then I'm going to ask you a question about each of the graphs that I'm putting up. I'm going to graph what's called the integer function. Okay, this is a function that it's also called a step function. I think you'll see why in a second. Okay, almost looks like these series of steps. What the integer function does is it rounds off any number you give it to the nearest, basically, integer. That's less. Okay, so this function rounds off any number that you give it to the closest integer it can. That's less. All right, so it's called the integer function. Okay, I just want you to understand that it almost looks like steps. Okay, and the last one, x squared minus 2x plus 4. This one's a little different than the other ones. And you'll see what I mean. I'm going to have to zoom out. Let's just go zoom 6. All right, so the question that I want to ask about each of these graphs is, can I trace them without lifting my pencil? Okay, how about the first one? Could I trace the entire graph without lifting my pencil? Nope. This is a graph that's in 2 pieces. I have to lift and go to the second piece. How about the step function? No, in fact, I have to lift my pencil every time I go to a new step. So here, there's a lot of times. And how about this one? Yeah, would I have to lift it or no? No, this is what we call a connected function. It's continuous. Okay, I don't have to lift my pencil at any point. So this one is, yes, You have to lift it. Yes and no. So whether or not you have to lift your pencil means something about the graph, which I just explained, and that has to do with continuity. Okay, so we say that a function is continuous if basically you can trace your pencil between 2 points. So you pick any 2 points on the graph and try to get from one point to the other following the graph. If you never lift your pencil, then that's called a continuous function. If you have to lift your pencil, then it's not continuous, it's discontinuous. Okay, and we could be a little bit more mathematical the way we describe continuous. I mean, lift your pencil, that's a little, I don't know, not exactly precise definition, but that's basically what it means. Okay. Now, it's possible that you could have a graph and it could be continuous on some intervals but discontinuous on other intervals. Okay, and I'm going to put up a picture and show you what I mean. Okay, I'm going to graph something similar to what you saw before. Okay, I'm going to graph 1 over x. And if you asked me, is that continuous or discontinuous, I'd say, well, you need to be a little more specific. Is it continuous everywhere? No. Is it continuous in some places? Yes. If you asked me to trace from here to here, I can trace on that interval without lifting my pencil. So from those 2 black dots, it is continuous. Okay? If you asked me to trace from here to here, that's continuous. Okay? From here to here, here to here. Tons of intervals where it's continuous. Okay? There's also a ton of intervals where it's discontinuous. All right? So what we're going to do now is just write down 2 intervals where this function is continuous and 2 intervals where it's discontinuous. Okay, so discontinuous means if you had me go from one x value to another, I'd have to lift my pencil to do that. Let's start with continuous. Okay, can anybody give me an interval with 2 x values that I could trace from on this graph without lifting my pencil? About Austin?
2 to 5.
Sure. I could trace from 2, which is right about here, to 5 without lifting my pencil. So from 2 to 5 is a continuous interval. It doesn't really matter if you use a bracket or parenthesis. Are you tracing from 2 or are you tracing from just after 2? Doesn't really matter. Okay, so we'll trace from just after 2, not including 2, up to 5. Okay. Can somebody else give me one more interval where this is a continuous interval? But Brad? -5, which is -1, 2, 3, 4, 5. So -5 to what number? -2, right about there. I can definitely trace between those 2 points without lifting my pencil. And this time I decided to go exactly from -5 to -2, and I included them. But it doesn't matter whether you include them or not. All right, now I want 2 intervals where it's discontinuous. Somebody give me an interval that if I tried to trace from these 2 x values, I would have to lift my pencil to do it. About John?
-2 to 2.
Yeah, -2 to 2. The key is, what number did he force me to try to go through that causes me to lift my pencil?
0.
0. At 0, we have what's called a discontinuity. I can't go through 0 without lifting my pencil. So basically in this one, you could pick any number that's negative and any number that's positive for your interval, and it's going to be discontinuous. It's not always negative and positive. You have to look at where your graph breaks apart. Okay? So another discontinuous interval, -8 to 1.6. Okay. All right, so the next function I want to look at was that step function. Okay, that one that looked like the integer function. So let's put that back in. And I want to find the longest interval in this function that is continuous. Yep, they are all the same length. So basically, I just want to know how long is that interval. If you need me to zoom in a little, I can. Can anybody tell how many units long it looks like each interval is?
1.
Yeah. Okay. In this particular function, the longest possible interval you could ever have that is continuous, it's 1 unit long. If you tried to give me an interval that's longer than 1 unit, I guarantee you it's discontinuous, because you would cause me to lift my pencil and jump up at least 1 step, maybe more steps. Okay. So the answer here is 1. All right, so there's 3 different ways that you can have what's called a discontinuity, or a point where you have to pick up your pencil and start your graph somewhere else. One is you can have a value that is not in the domain. Okay? You could have a fraction where you try to divide by 0. That causes a discontinuity. All right, so if I typed in 1 divided by x minus 3, where would I have a discontinuity?
3.
At 3. Okay, I can do zoom 6. Watch what happens when x is 3. Okay, I can't do it. Okay, so that's one way you get a discontinuity, an undefined value. Another way you can get a discontinuity is if your graph has a break in it. Okay, it's not that there's an undefined value here. Okay, the integer function can accept any number you want. Okay, as I said, all the integer function does is takes your number and rounds it down to the next lowest integer. Rounds down. So, is there any number you're not allowed to round down? No, you can take any number and round it down. Right? It's not like if you try to round down 4.7, you get an error, right? You can round that down to 4. Okay, so there's no numbers that you're not allowed to use. So nothing's undefined, but just the nature of the function, it causes breaks. Okay, because when you round, you skip all the decimals in between if you round by integers. Okay, and the last way you can have something, it's kind of like the first one. You get a value that's undefined, but it's a whole. It's not what we call an asymptote. This is a vertical asymptote. Okay, and the reason this one is tricky is because you will not see it on the screen. Okay, let me type that in. And we should know that there is a problem here somewhere. Okay, what value are you not allowed to use for x? Negative 2. You can't plug negative 2 in for x because you would divide by 0. But watch what happens if you graph this. Is it going to do something crazy at negative 2? Nope. It looks like it just went right through it without a problem. But what happens here is there's actually a hole right there. If you try to trace to negative 2, watch what happens. Doesn't give me a y value. Any other number, if I trace to it, it'll tell me the y value. Okay, negative 2.01. We can even go 1.99. Or negative 1.99. But the problem is I just can't do negative 2.
Is there a way you can see that? Like you can zoom in and see the whole?
Nope.
Because it's so small.
Yeah, it's like, because you can do negative 1.999999. See, that worked. It actually just rounded it. But that works fine. And you can do negative 2.0000000001. That'll work fine. It's like, it's so small you can't even see it. If we have to draw something with a hole, this is how we normally do it.
How do we know if it has a hole or not, though?
We exaggerate the hole so it looks bigger.
No. Like, how do you know you have it if you graph something?
Oh, well, you can't really tell from a graph. The only way you can tell is if you look at the original problem. Okay? So, looking at this original problem, watch what happens to the top. The top factors as x plus something, x plus something. Does anybody see what the top factors as?
2 and 1.
2 and 1. Look what just happened. You have an x plus 2 in the top, and you have an x plus 2 in the bottom. So whenever you factor, okay, when you've got a fraction, if you end up with the same factor in the top and the bottom, that's when you get a hole. So basically, this graph is exactly like this graph. Okay, watch it trace right over it perfectly. The only thing that's different between the graph in red and the graph in blue is the graph in blue has a small, like extremely small hole in it. The graph in red doesn't. Okay? And looking at the graph, you cannot tell that. You have to look back at the original problem. Okay, so those are the 3 ways that you can get discontinuities. The first 2, very easy to spot graphing it on the screen. The last one, it's impossible to spot on the screen. You have to know the algebra. Okay, so if I ask you tomorrow on the test if a function is continuous or what that means, you could say you can trace it without lifting your pencil. That's kind of the informal way. Or you can say it's a function that doesn't have any undefined values, it doesn't have any breaks, and it doesn't have any holes. That's the more formal way to say that a function is continuous. No undefined values, no breaks, no holes. So the last example that I did when we started this example right here, that's a polynomial. Okay. What's nice about polynomials is they are continuous all of the time. Okay, remember, polynomials are expressions that have positive exponents, no decimals as exponents, and they have coefficients, like 5x cubed minus 3x squared plus 8x. That's a polynomial. Okay. And we also mentioned that the domain of every polynomial is negative infinity to infinity. Okay, so polynomials are always continuous. If you have a function that is always continuous, okay, not just continuous on maybe certain intervals, but it's continuous on every single possible interval you could ever give me, that's called a continuous function. This one is not a continuous function. It's continuous in some spots, but it is not continuous on every single value from negative infinity to infinity. Okay, so any question on the idea of continuity? All right, so the second thing we're going to look at, we're going to tie in continuity with what's called the intermediate value property. Okay, it's a very simple concept. Okay, intermediate value property, intermediate means between, right? It has to do with values between 2 values. So let's say I had a pot of water, okay, and it's at 70, so like room temperature, 70 degrees. And I'm going to boil it. Okay, it boils at 212. What temperatures is the water going to go through in between 70 degrees and 212 as it starts to boil? what temperatures will it go through to get to boiling? Yep,
Um,
all of them, right? It's going to go through 81 degrees. It's going to go through 90.674 degrees. It's going to go through every single value from 70 all the way to 212 because boiling water is a continuous process. I don't care how fast you boil it. It doesn't all of a sudden go from 70 degrees to 160. It has to go through every single temperature in between. Okay? All the intermediate values. So the intermediate value theorem basically says if you have a continuous function, or like a continuous process, like boiling water, over a certain interval, and the interval that I gave you boiling water was like 70 to 212. Okay, so if you got a continuous function over a certain interval, then I guarantee you we will go through every y value in that interval. Okay, so as a picture, so you had something like this. Let's say that when I plug in A, that point is right there. Okay, that's one of my points. And let's say when you plug in B, some other number, you get a y value up here. Well, if it's a continuous function from this point to this point, I don't care how you get there. Okay, you can try to go back down and up and do whatever you want. But if it's a continuous function between these 2 points, I guarantee you're going to go through every y value from here to here. You have to. Okay, you can't skip a y value. Okay, like if this is negative 10 and up here is positive 40, at some point you're going to go through the y value 6. Okay, you have to. If you're going from negative 10 to 40 and it's continuous, you're going to go through every value in between. Okay, that's the intermediate value property. Any questions on that idea? Now that doesn't apply if a function is discontinuous, because discontinuous, I could just pick my pencil up and it's almost like I could warp somewhere else, right? But if you're continuous, you can't do that. You have to go through every value in between. Yeah, you could just warp. All right. So let's look at an example. It says, let f of x equal 3x minus 4. If you draw this, what kind of shape is this? Y equals 3x minus 4. Luke? Yeah, it's just a line, and Luke was saying with a slope. And this time it has a slope of 3. And it has a y-intercept of negative 4. Are lines continuous? Yes, lines are continuous. So if a function is continuous, yep, okay, we've got a continuous function. And I want to find a value of c. Okay, I'm going to call this value c, such that if I plug in this value for x, I end up with 15 for y. That's what I want to make happen. I want to find a number that I plug in for x, and when you plug that number into your function, you get 15 for y. Well, the first thing I have to check is, I know this line is continuous, but on this interval, does it go through 15? Between negative 10 and positive 10. Right? So what I'm going to do is I'm going to plug in negative 10, find the lowest y value. I'm going to plug in positive 10 and find the highest. And if 15 is in between those two, then I guarantee you we will hit it somewhere. Okay? So let's start by finding the lowest y value that we ever hit. Okay, if I plug in negative 10, I get 3 times negative 10 minus 4. So when I plug in negative 10 for y, what do I get? Yep, I get negative 34. Okay, so I know at some point I'm starting at negative 34. and let's see how high I go. Let's plug in an x value of 10. And what's the highest y value that I'm going to hit on this interval? 26. So now we can decide, is the question they asked us even possible? Will I go through a y value of 15? Yes. As I go from negative 34 to 26, and I never lift my pencil, I will go through 15 at some point. So now I can answer the question. Find out what value of x you would plug in and get 15 for y. Okay, so where would I put this 15? Would it go in for x or f of x? F of x. That's my y. Okay, so write 15 equals 3x minus 4. Now I guarantee you the answer I get is going to be between negative 10 and 10. It has to be. Okay? Somewhere. I don't know where, but I'm about to find out. And if you take 19 and divide by 3, it's about 6 1/3. So that is in between the interval. Now, if they asked me the question, find a value of c that you can plug in on the same interval so that when I plug in c, I get 70. Do I hit 70 on this interval? No. I'll hit it somewhere else. Maybe on the interval from 20 to 30 or 30 to 40 or somewhere else. But there is no value you could plug in for c on this interval and ever get 70. You're only going to get values between those two. Okay, so any questions on intermediate value property? Only applies to continuous functions. Okay. All right, and our last concept. So this one is kind of its own separate thing, okay, and it's called end behavior. Okay, what this is going to allow us to do is predict what a polynomial, or any function really, but we're going to focus on polynomials today, okay, what a polynomial looks like at the extreme ends of the function. Okay, so let's graph the function y equals x cubed. And let's examine the behavior on the very ends of the function. Okay, so I'm going to type in y equals x cubed. That's the simplest cubic function you can have. There's just nothing else, just x cubed. I'm going to hit graph. And there's my function. So when we're talking about end behavior, okay, we're looking at what's happening as on the very ends. Okay, on this particular function, what's happening is on the right side of the function, it's going up forever. Okay. On the left end of the function, it's going down forever. Okay. That's the end behavior of this function. On the right end, it's going up forever. On the left end, it's going down forever. And that's how you can write it. Okay. Put parentheses. On the left end, you can draw an arrow going down, meaning on the left side, what's happening to the y values? They go down. On the right side, what's happening to the y values? They go up. Okay. Any questions on that notation right there? Yep.
So that just, where's like the middle point? Where would you like, is it always going to be at 0?
So middle, we're not even thinking about with end behavior, but no, it won't always be at 0.
Alright. Well, I mean like the point where you determine what's left and what's right.
So just basically when you look at your function, you just, wherever it is, look at the right edge of it. So if it was over here, like that, this is the right edge, okay? Because it's what's happening as you go to the right. This is the left edge. Okay, because remember, these functions, they don't really stop right here. This one is just going to, keep going up that way, and this one's going to just keep curving down that way. It's going to go left and right forever. Not quickly, but slowly. Okay, so another way you can write exactly the same thing is this notation. This is called limit notation. And first, let me just describe it simply, and then I'll read it properly. This is saying what's happening to y as x heads to the right. As x gets bigger and bigger, what is happening to your y value? Okay, and the way you pronounce it is the limit of f of x as x approaches infinity. So let's see if we can answer it for this one. What's happening to my y values as x heads towards the right? What's happening to my y values? Yeah?
They increase at a greater rate.
And what are they approaching?
They are approaching infinity much faster than x is approaching infinity.
Yeah. So what's happening is as x heads to the right, my y values are approaching infinity. Now, what's happening to y as x is heading to the left? That's kind of making it simple.
Y heads towards negative infinity.
Yes. As the limit of y, as x approaches negative infinity is to the left, y is going down, which means it approaches negative infinity. Okay, so both of these notations mean the same thing. Limit notation is a little bit more formal. Arrows pointing up and down are a little less formal. And there's 4 basic end behaviors you can have for polynomials. You could either have both ends going up, okay, think of like a parabola, or flip that parabola over, both ends down, or one of each. One end up, one end down, or the other end up and the other end down. Okay, so I'm going to, rather than sketch it on the calculator, I'm going to just sketch it for you. X to the 4th looks like this. Kind of looks like a parabola, but it's a little flatter. What's the end behavior of f of x equals x to the 4th? Both up, both down, or one of each? Yep. So the end behavior here is up, up. If you were writing it in limit notation, like I did up here, what happens to y as x heads to the right? Y heads up. What happens to y as x heads to the left? X would be heading up. You'd get rid of the negative. Okay, so both directions, y approaches infinity on this one. How about this one? That's what y equals negative x to the 4th would look like. What's the end behavior there? Yeah, Nick? Both down. Down, down. So there's really an easy way to figure out what's happening. It all has to do with this exponent, and is the number in front of it a positive or a negative? Okay, so here's a chart that summarizes when you're going to have different end behaviors. If you have even exponents, the end behaviors go in the same direction, both up or both down. If you have odd exponents, you have one of each. To figure it out a little more precisely, then you look at the leading coefficient. If it's a positive leading coefficient and an even exponent, that's an up-up. Okay, that would be like x, like 2x squared. If it's a negative coefficient and an even exponent, it would be down, down. I don't know exactly what it's going to look like. I mean, I don't know if it's going to look, like this and go down, down, or if it's going to look like this and go down, down. But the big picture is they both are going to point down. Okay, and then an example like this would be positive coefficient, odd exponent, negative coefficient, odd exponent. Okay, so basically, when you want to know what a polynomial looks like, okay, all you have to do is look at the term with the highest exponent. Okay, the leading term controls everything. So if I gave you a problem on the test and I said, I want you to tell me which term here is the term that's going to control everything. Okay? In other words, tell me which term here is going to model the end behavior. It's this term right there. All these other terms don't matter. Okay? They might cause little twists and turns, but the thing that's really important is the term with the highest degree. It controls the end behavior. So, if you see a problem that asks you for what's called an end behavior model, write the term with the highest degree. And that's it. Okay? So, term with highest degree. That's called an end behavior model. Forget about everything else. Okay, so the homework tonight, it's the two problems that we didn't get to last night on increasing and decreasing. Okay, those are pretty quick on page 149. And then the rest of that will focus on continuity, intermediate value, and end behavior models. Okay, so on page 161, I want you to try 1 through 5, 9, 10, 12, 15, 16, 21 to 25, and 29 to 31. Okay, I will be here after school if anybody needs extra help. And we'll have our tests tomorrow.